Hello guys, welcome back to CFD College. I hope you are doing well and ready to learn. I'm Ashkan and this is another video of Fluid Mechanics 1. In this video I'm going to solve tutorial 11 of the course, which is presented in Concordia University. But it's useful to everyone. Every student wants to learn fluid mechanics, can enjoy this video, can learn something. In this tutorial, we have focus in chapter 8 of the fluid mechanics book written by Manson, which is related to flow inside pipes. So before starting the video, please subscribe the channel. Please share these videos with your friends if you find them useful. And I also have lots of videos on the YouTube channel you can enjoy that are related to numerical simulations using ANSYS Fluent. So let's start solving. This is the first problem number 21 of chapter 8. Here we have a pipe, oil of SG, specific gravity 0.87, and kinematic viscosity, nu, equals 2.2 times 10 to minus 4 square meter per second, flows through the vertical pipe, this pipe, at a rate of 4 times 10 to minus 4 cubic meters per second. So we have the flow rate, we have the kinematic viscosity, and we have the specific gravity of oil. Here this pipe is connected to a manometer, and we have a liquid here with SG of 1.3, and we want to find this manometer reading H. Okay, since we are dealing with a manometer, you know that we have to find the pressure difference between these 2 points. Let's say point 1 and point 2. We need pressure at point 1 and point 2, or we can use the pressure drop, the pressure difference between these points, and use the manometer equation to find this H. First, as you know, nu equals mu over rho. So kinematic viscosity is equal to dynamic viscosity divided by density. By having these definition, as you know, we have Reynolds number, rho v d over mu. So if you put rho in the denominator of the denominator, we have v d over mu over rho. So Reynolds number can be found from this formula, Vd over nu. So if you have kinematic viscosity, you can also find Reynolds number. So we have a fluid flow inside this pipe, so we should use energy equation. So between point 1 and 2, and we always follow the flow. If you remember the energy equation, P1 over gamma of oil, gamma of oil plus V1 square over 2G plus Z1, there is no pump, equals P2 over gamma of oil, the fluid inside the pipe, plus V2 square over 2G plus Z2 plus HL, the head loss, and there is no turbine. Okay, so now in this chapter, you know that you can find head loss. HL, it's equal to FL over D, diameter of the pipe, V square over 2G. So now you can calculate the head loss yourself. Okay, what do we know about these? We know that we want to find P1 minus P2, so pressures are not a problem. We have Z1 and Z2, so if Z1 equals, for example, 4, or let's say Z1 minus Z2 equals 4 meters, because we have it, let's say it's L. What do we know? Since diameter is fixed, is constant, it means that A1 equals A2, and since we have continuity, Q1 equals Q2, so V1 equals V2. So these terms are gone, they are cancelled. But to find HL, we need F and we need velocity. We have L, we have diameter, but we don't have velocity or friction coefficient. So velocity can be found from flow rate. We have Q. Q is equal to V times A, and so V is equal to Q over A. Q is 4.4 times 10 to minus 4 cubic meters per second over area pi over 4, 0.02 meters square. So velocity is equal to 1.27 meters per second. Now to find F, the friction coefficient, we should study that whether we are in laminar flow, whether we have a laminar flow or turbulent flow. So we have to calculate Reynolds number. Reynolds number equals Vd over nu. So we have velocity 1.27 meters per second. Diameter is 0.02 meters, and nu is 2.2 10 to minus 4 meters square per second. So Reynolds number is equal to 115, which is smaller than the critical Reynolds, which is between 2000 and 2300. It's a critical Reynolds number in pipe flow, in internal flow actually. So if the Reynolds number is less than this value, we can assume that we have laminar flow. We are in laminar region. Okay, since we are in laminar flow, so laminar flow, in laminar flow, the friction coefficient equals 64 over Reynolds number, which is equal to 64 over 115. So we can have friction coefficient, which is equal to 0.5565. Okay, now we have friction. Now we can solve energy equation, or let's say we can find HL first. HL, the head loss, equals F 0.5565 L over D. L is 4 meters. Diameter is 0.02 meters. V square 1.27 meters per second square over 2G, 2 times 9.81 meters per second square. So HL equals 9.15 meters. Now we can use energy equation. So P1 over gamma minus P2 over gamma equals Z2 minus Z1 plus HL so delta P over gamma. This is the gamma of oil. Equals HL minus L. Z2 minus Z1 is minus L. And so it's equal to 9.15 minus 4 equals 5.15. So delta P equals 5.15 times gamma of oil, which is specific gravity, times gamma of water, which is 1000. Gamma is rho g, kilogram per cubic meters times gravity. So this is gamma of water, which is equal to rho g. And this is gamma of oil. So delta P equals 43.7 kilonewton per square meter or kilopascal. Now we have delta P. We should use this manometer. We start from point 1 and move towards point B. Let's call this distance L1. So we should start from this point, move until the first interface. So the movement is downward, L1 plus H, and the fluid is the oil. So P1, we started from point 1, we move downward, so plus L1 plus H times gamma of oil. Then we should move upward for the distance of H, minus H times Sg, which is 1.3 times gamma of water. Then from this point to this point we move downward, and L minus L1. This is L minus L1. So the movement is downward, plus L minus L1 times gamma of oil, and then we are at point 2. So if you see, we have L1 gamma oil here, L1 gamma oil plus H gamma oil, and here we have L gamma oil minus L1 gamma of oil. So these are cancelled. So P1 minus P2 equals here. Okay, we should write down all of them. Minus H times gamma of oil plus 1.3 H gamma of water minus L times gamma of oil. Yes. So we have P1 minus P2, which is 43.7 10 to power 3 because it's kilonewton, or we can deal with kilonewton per meter square equals minus H times gamma of oil. Gamma of oil equals 87 times rho g, 9.81 kilonewton per cubic meter plus 1.3 H times gamma of water, which is 9.81 kilonewton per cubic meter, minus 4 times gamma of oil, which is 0.87 times 9.81 kilonewton per cubic meter. So now you can find H, and H equals 18.5 meters. So it's not difficult, but you have to think about Reynolds number, flow regime, whether it's turbulent or laminar, and then you should find the friction coefficient, and after that you have head loss and you can use energy equation. The second problem number 35 of chapter 8, water flows through a horizontal plastic pipe. When you have a plastic pipe, it means that roughness is 0. It's a smooth pipe with a diameter of 0.2. So we have the diameter, meters, at a velocity of, so we have velocity 10 centimeters per second or 0.1 meters per second. Determine the pressure drop per meter of pipe and the power lost to the friction per meter of pipe. Okay, so we have a pipe and we want to find the pressure drop first. So as I mentioned, you know that we should use energy equation because we have fluid flow. So P1, for example, if this is the pipe, 0.1 and 0.2, and for example it's 1 meters, but it's not important. So P1 over gamma plus V1 square over 2G plus Z1, there is no pump, equals P2 over gamma plus V2 square over 2G plus Z2, there is no turbine, but we have head loss, HL. You know that HL equals F times length over diameter times velocity square over 2G. Since we have a horizontal pipe, Z1 equals Z2. Since the diameter is fixed, V1 equals V2. We have a fixed diameter. So P1 over gamma minus P2 over gamma, which is equal to delta P over gamma, equals F L over D V square over 2G. So you know that gamma is rho G. So if you multiply both sides by rho G, delta P equals F L over D rho V square over 2. We have to solve this one. And as you know, we need F. So first we need to find Reynolds number. From table 1.6, you can see that density of water is 999 kilograms per cubic meter. Viscosity is 1.12 10 to minus 3 Newton second per meters square. So Reynolds number can be found as rho V D over mu. Rho is 999 kilograms per cubic meter. Velocity is 0.1 meters per second. Diameter is 0.2 meters. Viscosity is 1.12 10 to minus 3 Newton second per square meter. So Reynolds number equals 1.8 10 to power 4, which is far greater than 2100. So we have turbulent flow. In turbulent flow, you should use Moody Chart. Since here we have a plastic pipe, so we have smooth pipe. If you see the Moody Chart, you have a line, straight line, which is representing 64 over Reynolds number. For laminar flow. And what else? Here I think you have Reynolds number. Here is F, and here is epsilon over D, roughness divided by diameter, which is a dimensionless number. And you have many of these lines, but one of them is for smooth pipe. The lowest line is for smooth pipe. Okay, so you should use this line, and if you see the Moody chart with Reynolds number of 1.8 10 to power 4 and smooth pipe line, you can find F is equal to 0.026. Okay, now we have F, so we can find delta P. Delta P equals F 0.026, L which is 1 meter, diameter 0.2 meters, rho 999 kilogram per cubic meters, velocity 0.1 meters per second square, and divided by 2. So delta P equals 0.649 Pascal. And the power loss, the power loss equals P, or let's say power, this is power, not pressure. Power equals delta P times Q. So we need to find Q. Q is VA. V is 0.1 meters per second. A is the diameter of the, A is the cross-sectional area of the pipe. Pi over 4 times 0.2 meters square, which is equal to 3.14 10 to minus 3 cubic meters per second. So power equals 0.649 Pascal times 3.14 10 to minus 3 cubic meters per second. So power loss equals 2.04 times 10 to minus 3. Ten to minus 3 watt. And if you want to know, Pascal equals Newton per meter square. So we have Newton meters per second. Newton times meter is joule, and joule per second is watt. So it's the second problem, and we have one more problem. Problem number 42. In this problem, a 40 meters long, 10 and 30 In total, we have a 40 meter long, 12 millimeter diameter pipe. So the diameter is 12 millimeter. With the friction factor, so we have friction factor 0.02, is used to siphon 30 degrees centigrade water. So from a tank, as shown in the figure below. Determine the maximum value of H allowed if there is to be no cavitation within the house. Neglect minor losses. Okay. This minor losses means the entrance and the bend, not the head loss we have in the energy equation. That's major loss. So this is H. We have to find the maximum value for this, and we shouldn't have cavitation. So cavitation should not be occurred. As you know, the cavitation occurs where pressure, the local pressure, decrease to a value of to the value of vapor pressure, PV. Usually the pressure is much above this vapor pressure. That's why we don't have cavitation in the pipes in our houses or something like this. But here, since the water first goes up, it might happen. So just notice that cavitation will occur where we have the minimum pressure in the system. Where does this minimum pressure happen in this system? Here we have one point. Here we have the end, the outlet. We have certain pressure, and as we move towards inside the pipe, as you can see, the elevation is increasing. So because we are moving upward, this means that pressure is decreases. Why? Because as you know, in manometers, for example, when we go up, we have to, the pressure decreased, and that's why we subtract the pressure. For example, in manometers, we have this minus here, and for example, gamma H. It means because the pressure is decreasing as you move upward. In other words, you have to overcome the potential energy, because at this point with higher elevation, this point has more potential energy, so you have to overcome this. And it happens when the pressure turns into potential energy, and that's the reason why pressure is decreasing as you are moving upward. So now you know that when we start moving from this point towards the end, in this part of pipe, pressure is decreasing due to two factors. The first one is increase in the elevation, and the second one, which is everywhere, is head loss, is friction. So in the second section, when we are moving downward, the water moves downward, we have HL, the friction loss, pressure loss due to friction. But since the elevation is decreasing, the hydrostatic pressure is helping us. Actually, in other words, you don't need to overcome the potential energy. So here until this point, the pressure is decreasing by two factors, moving upward and head loss. But here in the second section, pressure will decrease a bit. I'm not telling that pressure is increasing. I mean, at least hydrostatic pressure will help us. So this is the critical point where both factors, hydrostatic pressure or potential energy, and head loss or loss due to friction, are working together and decrease the pressure much. So this is the critical point in the system. So first, let's assume that we have a cavitation at this point 3, because here at this free surface we have 0.1, and here at this outlet we have 0.2. So first we assume that at 0.3 we have cavitation, and then we check whether we have cavitation in, for example, in this point, at this point. Okay. Why we check this point, not the point in the first section of the pipe? Because we are sure that pressure at 0.3 is less than pressure at point, for example, A. But we are not sure about that for this point, for example, point B. Or 0.4, let's say, 0.4. So point A is not a problem. So first, we assume that we have cavitation at 0.3. It means that P3 equals vapor pressure. For water at 30 degrees Celsius, we know that vapor pressure is 4.243 kilopascal absolute. As you remember, I've mentioned it so many times. When you are dealing with cavitation, you should use absolute pressure. And also density is 995.7 kilograms per cubic meter. Okay, so first we write down the energy equation between 0.1 and 0.3. Sorry for that. So P1 over gamma plus V1 square over 2G plus Z1, there is no pump, equals P3 over gamma plus V3 square over 2G plus Z3 plus head loss, which is FL over D V3 square over 2G. Okay, what do we know? At point A, we have a free surface. Usually you say that pressure is 0, but here we are working on cavitation. So pressure should be in absolute value. So P1 equals 101 kilopascal, ABS, absolute. As you know, Z1 is 3 meters. If we put Z-axis here, and Z3 equals 7 meters. We know that pressure at 0.3 equals vapor pressure. What else? We have the friction coefficient, and we also know that V1 is 0 because it's a free surface. So only this term is gone. Okay, let's put the values inside the equation. So P1 minus P3 over gamma plus Z1 minus Z3 equals V free squared, because V free is an unknown, over 2G plus FL over D V free square over 2G. So if we factor out V free over 2G, we will have 1 plus FL over D times V free square over 2G. So now the values, P1 is 101 minus PV is 4.243, both in kilopascal, so kilonewton per cubic meters, over gamma of water, 9.77 kilonewton per cubic meters, plus 3 meters minus 7 meters equaled 1 plus 0.02 times L, which is 10 meters, over D, which is 0.012 meters. We are moving from point 1 to point 3, and there is no minor loss at the inlet, but the L, the length of this part of tube is 10 meters, times V free square over 2 times 9.81 meters per second square. So from this you can find V free equals 2.56 meters per second. Now we know that if we have cavitation at point 3, which was the critical point, which is actually the critical point in the system that we have, velocity should be 2.56. Okay, now if we write down the energy equation between point 1 and point 2, we can find H, because now we know the velocity. We have velocity at point 3, and since the diameter of the pipe is fixed, it means that V2, actually velocity at any point, is equal to V3, 2.56. So now between point 1 and point 2, P1 over gamma plus V1 square over 2G plus Z1 equals P2 over gamma plus V2 square over 2G plus Z2 plus HL, which is FL over D V2 square over 2G. Be careful that here from point 1 to point 2, L is 40 meters. Now since at point 1 and at point 2 we don't have cavitation, you can use gauge pressure for P1 and P2, but don't do that. What do we know? P1 is atmospheric, and also P2 because it's an outlet. So P1 equals P2 equals 101 kilopascal. It means that these terms are gone. We also know that, we also know that V1 is 0 because it's free surface. We know velocity, V2 equals 2.56 meters per second. Z1 and Z2. Z1 is free. This is the axis. But Z2 is minus H. So Z1 is 3 meters. Z2 is minus H. Now we can find H. So Z1 equals Z2 plus, if we factor out again, 1 plus FL over D V2 square over 2G. So 3 meters equals minus H plus 1 plus 0.02 times L is 40 meters. Diameter is 0.012 meters. V is 2.56 meters per second square over 2 times G, 9.81 meters per second square. So from this you can find H. The maximum H actually equals 19.6 meters. So here, now we know that if we have cavitation at point 3, which is the critical point with lower pressure in our system, the velocity in the pipe is 2.56 and the maximum H, the H is 19.6 meters. But as I mentioned earlier, we have to check whether we have cavitation somewhere here between point 3 and point 2. Or let's say we want to check the assumption that we have cavitation at point 3, that the point 3 has the minimum pressure in the system. This was the assumption that we made. So we assume point 4 somewhere here. By this assumption, we will have this. So this is point. This is point 3. This is point 2. Here is point 4, for example. This length is L. And we have this triangle. So if we put z-axis here, this is z4, and this is h plus 7. Meters. Okay, so we want to check the minimum pressure. Actually, we want to see if the minimum pressure occurs at point 3 or not. So let's write down the energy equation between point 4 at point and point 2. So P4 over gamma plus V4 square over 2G plus Z4 equals P2 over gamma plus V2 square over 2G plus Z2 plus head loss, which is FL over D V2 square or V4 square, they are the same, over 2G. So what do we know? We know that P2 is atmospheric. Here, as I mentioned, since there is no cavitation, we are not having vapor pressure actually for point 4 and point 2, so we can use gauge pressure. So P2 equals 0, V2 equals V4 equals V. So this term is 0, and these terms are cancelled. Z2 is 0, Z4 is L. Oh, no, it's not L, sorry. 0, Z4. And what else? V is 2.56 meters per second. That's it, I think. But we should find Z4 based on L. So if we use this triangle, we can understand that L over Z4 equals 30 over 26.6h plus 7 is 26.6, and the total length from point 3 to point 2 is 30 meters. So from this we can find Z4, or L, equals 1.128 Z4. Okay, so now if we put the values in the equation, and you know that gamma of water equals 9.8 kilonewton per cubic meters. So P4 over gamma plus Z4 equals FL over D V square over 2G. So P4 equals minus Z4 times gamma plus FL over D rho V square over 2, not 2G, because I multiply both sides by the gamma. So P4 equals minus 9.8 kilonewton per cubic meters times Z4 plus F 0.02 L, which is 1.128 Z4 over D, diameter 0.012, times rho 999 kilograms per cubic meter times velocity square over 2. So P4 equals minus 3650 Z4. What does it mean? It means that as we move upward in this direction, actually as Z4 increases, the pressure decreases. It means that P2 and P4 is greater than P3. So actually the first assumption that we made, which was we have the minimum pressure at point 3, is correct, and the minimum pressure occurs at point 3. So at point 3 is the only point that we can have cavitation. So all the calculations are correct and we don't need to do anything else. So that's it. This is the end of this video. Tutorial number 11 of Fluid Mechanics 1. I hope you enjoyed it. If so, please subscribe the channel, hit the notification bell, give us a thumbs up, and share these videos with your friends in future semesters. Thank you for watching the video. Until the next one, take care of yourselves and bye bye.